Hello. Today I want to talk about the very last webwork problem. It's problem 11 in set 17. And this involves a nonlinear system of two first-order ordinary differential equations. This is a predator-prey system, also called a Lotka-Volterra system of equations. All right. The idea here is you have a population of rabbits, R of t, and foxes, F of t, and they're modeled by these equations. Okay, dr dt is a positive constant times r minus some constant times r times f. And df dt is a negative constant times f plus a positive constant times r times f. Okay, so this r times f is what makes it nonlinear, and our eigenvalues and eigenvectors don't help us with this. All right, so let's think a little bit about why this happens. Okay, so what if there, and this is sort of like the population on an island or something, some isolated spot. So let's try to think about why these equations are the way they are. So first, suppose I had no foxes at all, only rabbits. Well, we know what rabbits do, they multiply, right? So if I think about what happens if f equals 0, so if f equals 0, we get dr dt is 0.4r, or r is r naught e to the 0.4t. The rabbits grow exponentially, right? The most important ODE. Dr dt is a constant times r. Okay. Now, what happens if there are no rabbits and just foxes? Well, the foxes will starve to death. Okay, right? So and we can see that by this. If the rabbits are 0, there's no rabbits, then df dt is a negative constant, negative 0.2f. So f equals f naught e to the minus 0.2t. So what happens here is here's t, and here's f. The foxes start off with some fox population, and they decay to 0. They die away. Okay, now this is just, sorry, minus 0.2t. This is just a model, right? After a while, you're not going to have 0.03 foxes. So, and this is what modeling is like, right? Okay. So now let's think. So that's these parts. Now let's think about this r times f. Okay. So the amount of times per second that a rabbit and a fox encounter each other is proportional to how many rabbits there are and how many foxes there are. If there are twice as many rabbits, then there are twice as many eating events. Twice as many foxes, twice as many eating events, right? And what happens if a rabbit and a fox encounter each other? Well, the fox eats the rabbit. And that has the effect of decreasing the rabbit population as a negative sign, and has the rabbit and the fox meeting has the effect of increasing the fox population. Okay. By the way, while we're talking about rabbits and foxes, I've got a little joke here, right? So a Catholic priest, a Lutheran pastor, and a rabbit walk into a bar. And the rabbit says, "I think I'm a typo." All right, let's go on. So let's think about now this problem here. So you're asked to do two things. You have a problem very much like this. You have aphids and ladybugs. And the aphids in this case are the predators, and the ladybugs are the prey. Right? But I'll use this rabbit and fox, which is the Lotka Volterra was originally thinking about rabbits and foxes, actually in a real system. Actually, the first equation, if you look up this on Wikipedia, this actually was originally done for chemical reactions. So I have a concentration of two different chemicals. The rate of the chemical reaction is going to be proportional to the product of those two concentrations, for the same reason of the rabbits and foxes. The amount of times the molecules hit each other is proportional to the product of the two concentrations. So anyway, let's go on with this problem. Actually, I want to do this problem part B first. Now, even though this is a system of two first order ODEs, one of the things I haven't mentioned yet is very important that there's no time here explicitly in this, right? R is R of t, a function of t. F is a function of t, but there's no explicit time in here, okay? So that has the effect of I can kind of eliminate time and think about the FR plane, which I'll show you pictures of that. But let's get to this. df dr is equal to df dt, all divided by dr dt. I won't actually justify this, but I think it kind of makes sense. You can sort of formally think about multiplying top and bottom by dt. And if I multiply top and bottom by t, the dt's cancel, and I get df on the top and dr on the bottom. Okay? So that is going to be equal just df dt, so I have minus 0.2f plus 0.005 rf divided by dr dt, 0.4r minus 0.05 rf. And that's all there is to it. Actually, probably the hardest part of this problem is making sure you enter it correctly into webwork. You probably want to put parentheses around the top and the bottom when you enter this into webwork. Okay. And I'll show you this in a little bit. It looks kind of complicated, but this also has the effect of we can sometimes use our techniques way back in the first part of the course. This is just a first order ODE, thinking of f as a function of r. And you can use some of those techniques. Okay. So you've taken care of that. Now let's think about the equilibrium populations. The equilibrium populations is the place where if there's that many rabbits, that many foxes, it will just stay put. The time rate of change will be 0. And we've had this before with a single. We called it autonomous. This is an autonomous system, no explicit t in it. So basically what we want to do is solve dr dt equals 0 and df dt equals 0 for r and f. Find the values of r and f, rabbits and fox population, where it's going to stay put. It won't change with time if that's the initial conditions. All right, to aid that, let me first factor these equations, right? There's an r in both of these. So I factor out the r, and I get 0.4 minus 0.05 f, right? We get the r times the f when I distribute. Okay? And then this thing here is, there's an f in both the terms. So I factor out the f and get minus 0.2 plus 0.005 r. Okay? All right. So what is this system of equations then? We need to solve dr dt is 0, which is r times 0.4 minus 0.05 f, that equals 0. And we also need that f times negative 0.2 plus 0.005 r equals 0. That's the parentheses. That's the condition that the r dt is 0 and the f dt is 0. So, and I factored it here because that, when we solve equations, we love to factor them, because if a times b is 0, then either a is 0 or b is 0, or perhaps both, right? So if that times that is 0, we get r equals 0, or let's, right, 0.4 minus 0.05 f equals 0. And I'm going to put this in parentheses because we have this or that, and we have the other one. So when I have a bunch of expressions with ands and ors in it, sometimes you have to do parentheses. And then what do I have here? Either f equals 0 or negative 0.2 plus 0.005 r equals 0. Okay? All right. So let's think about this. If I take this and solve this part here, I get f is equal to 0.4 over 0.05. Right? So I kind of bring this to one side, the minus signs are going, divide by 0.05. So let's multiply top and bottom by 100. Move that over twice, I get 2.40 over 5. That's 8. And then what is this? So I can solve this one for r. I get r is plus 0.2 over 0.005. Once I have to move the decimal point over 3 places, multiply top and bottom by 1,000, move it 1, 2, 3, I get 200 over 5, or 40. All right. So let's continue with this. I've kind of run out of room. We'll erase the system of equations for the ODE, and we're back to the equations for equilibrium. That's that. Those are both the 0. And let's have the and. Got to have both of them 0 at the same time. So let's summarize what we got. We have r equals 0 or f equals 8. And we have f equals 0 or r equals 40. Okay, so takes a little bit of logic here to figure out what are the solutions, okay? Remember, we have a nonlinear system of equations. We don't have our matrix methods. I mean, solving a linear system of equations is well studied. And with a nonlinear system of equations, you sort of have to do it by hook or by crook. Okay. All right, so here, one of these happens. Suppose we have r equals 0. If r equals 0, then we also have to have f equals 0 or r equals 40. But r equals 40 is right out because r is 0. So we have f is 0. So one of the solutions to this is r equals 0 and f equals 0. Okay. Or we can also have, well, let me see, this gives r comma f equals 0, 0 as a solution. let's get rid of this, as one equilibrium. Let's think about this. Maybe you could have thought about this from the very beginning, right? If I have this island here that has no rabbits and no foxes, it will just stay put. That's an equilibrium solution. They're both dead, both extinct. That's one possibility. Another possibility is that f equals 8, and if f equals 8, f can't be 0, so we have r equals 40. This gives you want to put them in the ordered pair, r first and then f, and this is equal to 48. So we have 40 rabbits and 8 foxes, and that will be another equilibrium. Okay, so right, it kind of makes sense. Usually with predators and prey, you have fewer predators, you have 8 foxes, and more of the rabbits that they eat. Okay, those numbers kind of make sense, right? All right, so the way that you would enter that into webwork is you would say, 0, 0, comma, 48. All right, so I want to show you some pictures of this. We'll go share the screen. Okay, first I've got here the Lotka-Volterra equations. I'll let you look at that on Wikipedia if you want. And what happens, here's some, this is like lynxes and snowshoe hares and lynxes. The hares are like the rabbits and the lynxes are like the foxes. Okay, but let's go to our page, which has our favorite program. Okay, this program actually has stored in it some cases. Here we've got predator-prey. So we're thinking about the predator-prey system. This is exactly the predator-prey equations that I showed you at first. They're using small r, where I use big R and small f, but okay. So this is something that we see here. This is R. Or if the rabbits will just grow exponentially, if there's no foxes will decay exponentially if there's no rabbits. And it turns out that actually we've got this solution right in the middle, this equilibrium solution, which is pretty close to 40. Well, with the equilibrium is exactly 40 rabbits and 8 foxes. And what happens here actually is in the plane here, the solution goes in circles around there. So the rabbit population oscillates and the fox population oscillates both. And that's why they, let's go back to here. We got this little picture of the rabbits in the fox population, or the lynx and the whatever. Populations go up and down. Okay. So one more thing about this is that here they've done exactly your part B of the problem. Here they've actually found a single ODE for dy dx, and that's kind of what I did down at the bottom. Is gone now. We just get you see how the populations, the curves look exactly the same, but this is now thinking about dy versus dx. And all right, so it looks kind of weird, right? Because even with the switching on, which makes it better, the as a differential equation, this is kind of strange, but at least it does give you we'll clear all the curves, but it does give you the same exact slope lines here as you got the direction field lines over here, right? We can go from here. These directions have arrows on them, but here you see the slope lines don't, okay? But actually one way that we could show that actually all these solution curves lie on closed curves is think of this single first order ODE as we did in the beginning of the class. And this actually turns out to have a constant of the motion. These curves all lie on some function of x and y equals a constant. That's why we see these closed curves. These are contours of a constant function of two variables. All right, so I've talked a lot more about what you really need to do to solve this problem, but it's kind of fun, and it's one of the reasons we do these systems of ODEs. And in fact, probably I'll give you a bonus little mini lecture tomorrow about the system like this that models the COVID-19 or any outbreak of infectious disease. That's the SIR model, the susceptible, the infected, and the recovered population. Okay, all right, bye.